Now we are going ahead, and that is a eutectoid system. Eutectoid system. Okay. So what is the difference between? So eutectoid represents the equilibrium of a system whose composition whose component are subject to an allotropic transformation. Means allotropic means, I mean, how they can convert into different phases. Okay, that is allotropic, and sometimes they have the same phase, but their you know crystal structure gets changed. Okay, suppose, I mean, if you are cooling something, okay, and cooling some material, and that is in a solid state as well, okay, but their internal solid structures gets changed. Suppose it was earlier FCC, means face centered cubic structure, and once you have heated them, then it got converted into BCC, I mean body centered cubic structures. Or reverse of that, if you have the in a solid state, and you are just making them cool down because they are on a higher temperature. Once you are making them cool, that would be your then it could convert it. It's internal, though you would be not able to see through your naked eye, that you would be see that, yeah, it's just a cooling down material. But during that cooling, okay, throughout the cooling, your material is in solid state. They are not changing their phase, but their internal structure is being changed. That changing is also known as your allotropic. Okay, so that is allotrop. Sometimes you have a solid or you have a liquid, but their internal structure is getting changed, and that you can that you can see through the microscope. Okay, so it indicates the decomposition of the solid solution into the two other solids. Okay, so eutectoid reaction is of form. What does it mean? So, I mean, in the eutectic system, you have a liquid, and that is being converted into solid of two kinds, right? But here you have a liquid, you have a solid state. But after cooling, or after cooling, you are getting another two different kind of solid state. So one solid is being converted into two different solid. This is your eutectide system, and reverse of that also possible, because if the solid is being cooled, then it will be produce the two different kind of solid. But reverse of that, if you have a two solids and their composition, and then you are heating them, then it would be directly converted into a different solid. They're not getting converted into liquid. So their phase is same. Phase is also same, but their you know separation is different. I mean, here it was as a single solid. Okay, but when you are cooling them, then it got converted into two solids. Okay, so here it is representation. If you have the gamma, which is the name of your any solid material, okay, and that would be of alloy as differently. Okay, that's why it would be converted into two different solid. Otherwise, pure metal will not get converted into two different solid. Okay, so this is the study of about alloys. So when you are cooling them, okay, it will be converted into two different solid of alloy. And reverse of that, if you have two different solids of alloy, then you can heat them together, and it will be converted into the single solid. Okay, so this is what eutectoid system. Okay, here you can see, so this particular point, the B, is the eutectoid system. Okay, so how? See, this is your liquidus line. As you can see, A to E is liquidus line, and again E to C is the liquidus line. And what E suggests here, if you have, you know, uh, if you were, able to see what I have already made you know about eutectic system, then you could say it is a eutectic point, because this is the point you can see. Observe, if A to E is a liquidus line and E to C is a liquidus line, and what about this line? This particular line throughout this is a solidus line, because or you can say all the things and the material that is below that particular line is in the form of solid state. Okay, so this is a solidus solidus line, and the point where the liquid can convert it into the solid directly. It's known as your eutectic point. So this is your eutectic point, and the B point, it is your eutectoid point. How? This is the solid. I mean, this is solid, and this solid is going to convert it into. You see, this is solid. Okay, so solid. I mean, this is the liquid line. This is the solid plus liquid line. Here you have a solid, and now at this point you are getting converted into directly to, I'm sorry, alpha plus beta. Yeah. In this particular diagram, E is the eutectic point and B is your eutectoid point. Okay, so this is a different kind of for the solids, solidus, and this is a different, as you can see in this particular diagram, this is your composition, this is your temperature. Okay, so this is, the particular example of PB, lead, and SN, yani tin. Okay, so if you have the alloy of the PB and SN, lead and tin, okay, then this is the particular combination of that. I mean, if 20%, as you can see, this is increasing. It means the tin is increasing in this way. Okay, so tin is basically 20%, and 80% is your PV. Okay, this particular composition, the temperature is 183 degrees C. Then you would be reaching at your eutectoid point. If you talk about the eutectic point, then you have the tin, which is 60%, and rest 40% is your PB. Okay, so 40% is your PB. Then this and the temperature is remains the same, 183 degrees C. So at the same temperature, okay, but for the different combination of your composition, you are getting two different points. First one is the eutectoid point, and second you get a eutectic point together. In the example of SNPB, sorry, PB SN. PB means the lid and SN means tin. Okay, different points are there, but we are basically having, uh, you know, concern of these two terms. Okay.